Let's talk about the second derivative test. So we already know about the first derivative test, where we check for critical points by setting the first derivative equal to 0. And then we test with a table to the left and right to determine if it was increasing 0 and decreasing, which would be a max, relative max, or whether it was decreasing 0 and then increasing, which would be a relative min, right? So we can see that here. So on the top graph here, we know that's a min because the slope is negative, then the slope is 0, and the slope is positive, right? So we found this one, and of course the one up here too. We found both these relative minimum and maximum, or really critical points first, by setting the first derivative equal to 0. So let's create the first derivative here for this cubic function which I graphed. And it's important to say that we're not going to have these graphs when we do the problems, but by looking at the graphs on this example problem first, the two new topics, the second derivative test and the concavity, will become clear. But let's first just review the first derivative test. So let's take the first derivative, so f prime of x, just using the power rule here, would be 3 x squared plus 12x plus 9. Okay, and you know what we would do, right? We would set it equal to 0. So we would find the critical points. And when we do the second derivative test, we're going to do the exact same thing. We absolutely have to do this, right? So I'm going to GCF out of 3 to make my life easier. And then when we reverse FOIL this, of course, and I'll leave the 3 here, we're going to get x plus 3, x plus 1, very easy. Which means, right, therefore, we know that the CPs, the critical points, are at x equals -1 and x equals -3. All right, now I'm not going to go through, there's our 2 points, by the way, right? When x equals -3 and when x equals -1. You can get these y values by plugging into the original equation. We don't really need to do that right now. So we do the first derivative test. We usually set up a table to do it, but just visually we can see it here that the slope went from positive to negative. It has to change. And of course it went through 0. That was the slope of 0. And down here we went from negative slopes to 0 slopes to positive slopes. So we knew from the first derivative test without actually doing it, because we've already done it, that this is a relative min, to use the short terms, and this is a relative max. Of course, that's just the x value. In order to get the y value, you plug them back into the original equation. Okay, but there's a couple of things. There's an easier way, actually, although the reason why we need both is it doesn't always work. There's an easier way to do this rather than setting up a huge table called the second derivative test. Okay? So let's take a look at what happens to the first derivative, first of all. You can see here that when the first derivative is equal to 0, right, that's what this is. That's what this is telling us. It's saying, hey, look, it's set it equal to 0. So again, the x-axis is way up top here on this graph. And we found out that that happened here and here. Okay? And that's how we got these critical points. But if we take another derivative, if we take the second derivative, let's take a look at that graph. So in other words, if we take the slope of that graph, right, if I take the slope of this graph, f prime, I get f double prime, and we get 6x plus 12. Okay, now we're going to come back to that in a second. Let's go back up to the original function here. And let's talk about two things. Well, first we're going to talk about concavity, okay? Because that's what the second derivative actually tells us. So the graph here is concave down from here to right there, okay? So this is called concave down. You can see it. It's like a bowl upside down. Okay, and then from that point here to this point here, it's concave up. This is just a visual thing, right? Concave up, right? So it's a bowl up. This is like a big bowl, right? The bowl of soup, whatever, like this, right? Bowl up, that's concave up. And this is a bowl down, concave down. And the point where that changes, this is called a point of inflection, okay? This is called a point of inflection, or poi. We call it poise. Point of inflection is where the bowls change, okay? It's also called a poi for short, makes it easier to talk about. And what's important about this, what's great about this, is that relative mins always happen in a bowl up, see? And relative maxes always happen in a bowl down. And what's really cool about that is the second derivative. So let's take a look at the second derivative. See? F double prime of x down here at the bottom is negative from here to here, okay? Or if I wanted to show the x values, of course I could do that too. So in other words, all x values below here, because this goes way down. This is a line, right? 6x plus 12. So everything to the left of negative 2 is negative, right? All the y values are negative from there to there. So again, anywhere on this line this way, it's negative. On the top, and look, I'm trying to match the colors here for you. So the top here, all of this is positive. All the y values of the second derivative are positive. And if you look to the top graph, right? If you look to the top graph, this, right? Oh, I want to use green, sorry. This whole section here, right? This whole section here. Oops, I didn't want to do that. So this section here matches this section up here. See? In other words, wherever the second derivative is positive, which is from x equals 2 all the way forever this way, right? So I'm sorry, negative 2. So negative 2 to, or beyond negative 2, so greater than negative 2. So negative 1.99, negative 1, 0, 1, 2. So in other words, everything past this point up here, see, past this point up here, is all concave up. So what's important is the second derivative predicts, right? Second derivative up here, this should be green. This, on this graph, predicts concave up on F, not F prime, not F double prime, on F, okay? And this predicts concave up on F, okay? And you can see it. If you go to the top of the graph here, of course, you can see where it's concave down and concave up. And one more thing, which we will actually talk about in the next video, but a little foreshadowing here, is that's the poi, right? That's the poi. So the poi happens at x equals negative 2. Okay, the concave up happens when x is less than negative 2. And the concave down, concave, oh, I wrote it wrong, sorry. This is concave down, my bad. Concave down is here, so, and this happens when x is less than negative 2, my bad. And this happens when x is greater than negative 2, right? So when x is greater than negative 2, f double prime of x is positive. And when x is less than negative 2, when x is less than negative 2, f double prime of x is negative, and that means concave down. So what does that mean? What that means is, instead of doing the first derivative test for these two CPs that we found earlier, right, we can do the second derivative test. In other words, let's take f double prime. F double prime, which we already did. It's in blue down here, right? So f double prime is 6x plus 12. Okay, and all I need to do is to plug these two values in and see what the concavity is, okay? So again, we're pretending We're pretending we don't know this, right? We're pretending we don't know this. We're pretending we don't know that. We didn't do the first derivative test. Of course we know what it is, but we're pretending we didn't. So all we have to do is say, well, what happens when f double prime is equal to -1? See, we'll take this value here and plug it in. What happens? And then next we'll do f double prime is equal to -3, our other critical point, see? And that will tell us what's going on. So when we plug f double prime -1 in, right, I get 6 times -1 plus 12, right, equals positive, right? This -6 plus 12 is 6. 6, which is positive, right? And here, right, f double prime of -3 is 6 times -3 plus 12. So that's -18 plus 12 is -6, right? So this is negative. Okay, positive means concave up. Concave up, okay? Which means, concave up means this. See, concave up over on the F graph, concave up means a min. So it's kind of the opposite. You got to be ready for that. It's a min, right? So then we say conclusion is a relative min. Which we knew, right? We knew this already. And negative means concave down. Concave down. What does concave down look like? It's up here in the original graph. Concave down. Concave down happens in the original graph here where there's a maximum. So then conclusion is relative max. Okay, so much easier than the first derivative test. The only thing is that sometimes it fails. And these well-behaved polynomials, it's not going to fail. It's going to work perfectly. But sometimes it fails. And we have to be aware of that. And when that fails, in other words, if this was to equal 0, for example, then we have to go back and do the first derivative test like we usually do. But it's always easier to try the second derivative test. Okay? And by the way, this breaking point where it's neither, right, where it changes, which is what we call a poi, you get that by setting this equal to 0. Okay? And I'm going to GCF here. So you can see that that happens at x equals -2, which is exactly what we expected from the original graph. So that's how you find a poi. You just have to make sure that it actually changes on both sides. So just because it's 0 doesn't mean it's a poi. It's actually a pupoi. So we call this a potential point of inflection until we confirm, which is easy from the graph here, until we confirm that to the left and right of this you get two different concavities, right? You get concave up and you get concave down. Okay, so let's try a problem on your own. And again, we won't be so lucky to have the graphs. So let's try this problem. This is a function p of t. It's a quartic function. And you're asked to find the relative maxima and minima. So I want you to do this problem on your own, but just a quick reminder, you're gonna find the first derivative. You're going to set it equal to 0. And you're going to find the critical points, and then you're going to do what I did in the previous slide, which was to set the second derivative, right? Plug in those values for the second derivative and see what you get. See if you get a positive or negative, and then determine if that makes it concave up or down, which then determines if it makes it a relative max or min. So go ahead and give that a shot. Pause the video, and then I'll do the problem. Okay, so the first derivative is, which we're going to set equal to 0, is 12t cubed minus 60t squared. And we're going to factor that, right? So we're going to GCF out of 12t squared. And that's going to leave us with t minus 5. Okay, so our CPs, and this is no different right now than the first derivative test, is t equals 0 and t equals 5. Okay, so we have two potential relative max or mins, right? And normally what you would do in the first derivative test is you would plug in a number like -1, -1, and 1, and then 6, right? So you'd find out what's happening on either side of the 5 and either side of the 0. And you can do that and it'll work fine. And we may have to do that if the second derivative test fails. So like I said, it doesn't always work. So let's do the second derivative test though. What we're going to do instead, which is generally easier, is take the second derivative. Oops, sorry, minus 120. Okay, sorry, 36t squared minus 120t. Okay, we're going to factor that. We're going to factor out a 12, I think. Sorry, 12t, and we're going to get 3t minus 10. You don't have to factor the second derivative, but I find it's a lot easier because when you go to plug in numbers, it's much easier than multiplying, squaring and multiplying by 136 or multiplying by 120, because all we care about is if it's positive or negative. I don't really care about the actual p-value or really p double prime value, right? I don't care. I just want to know if it's positive or negative. And when you're looking for the poi, right, or the poi, which I talked about quickly in the other video, you're often setting this equal to 0, so you'll already have this factored in more complex problems, so you'll probably have it available to you. So let's do it. Let's plug in p double prime. Let's plug in 0, p double prime, so p double prime of 0. And if I just look, right, by inspection, you don't have to really go crazy here. You don't have to find the actual value. If I put in a 0 here for t, I get -10 times 0 is 0. Okay? Now we'll talk about what that means in a second. And let's plug in 5, right? And we'll do this one first. So p double prime of 5. So you plug in 5, you're going to get 15 minus 10 is positive, times 12 times 5, 60. Positive times positive is positive. See? Notice I don't need to put the actual value there. It's not important. Because sometimes it's just a pain in the neck to find the value. Or it takes an extra 10 seconds, which we don't have, right? So if it's positive, we know this is concave up. Concave up. Notice I'm avoiding the other one for now. We're going to get right back to that in a second. Okay, this is concave up. And concave up means, right, concave up means a bowl up, which means this point at the bottom here, this point is a min, right, or a relative min. Okay, so my conclusion is this is a relative min. Notice I didn't have to do the first derivative test. I didn't have to plug in two values. I just plugged in one quick value to the second derivative. Unfortunately, this conclusion is not sure, right? Or, yeah, inconclusive really is what you want to write, but I'm just put not sure. What really happens is this is probably a poi, right? It's definitely a poi. That means it's a potential point of inflection. And most likely it's actually going to be a point of inflection if we were to test it, if we were to plug in a number to the left of 0 and a number to the right of 0. So we already have one here, it's positive. And if I plug in -1, you'll see I'll get negative, and this will be a poi. But we're not really doing that in this video. All we're talking about is the fact that it failed, right? So the second derivative test, as I warned you, failed. It worked fine for 5. We found out that's a relative min, but it failed for this. So we have to resort back to the first derivative test. And what's nice is, though, we only have to do it for 0, right? We only have to do it around 0. So we're going to test to the right of 0, and to the left of 0 and the right of 0, right? That's my t value, okay? And then I'm going to just plug in f prime of t, and we're going to see what we get, okay? So remember, back to the first derivative test, which is to plug it into here. Again, I'm going to use the factored version here, right? This factored version is nice. So we'll use the factored version. And when you plug -1 in, I get -6, right? And this is +1, so 12 times -6, I get a negative number. When I plug in 0, of course, I get 0, because that was the whole point of it, right? That's how we knew it was a CP. This is a CP. We're testing a CP. And when I plug in 1, I also get negative, right? So 1 minus 5 is negative 4 times 12. It's also a negative number. See? So normally, if I was doing the first derivative test, which I am doing, normally when I'm doing the first derivative test, I would look for negative to positive, right? Or positive to negative, right? So that would be a maximum, right? And this, oops, and this would be, if it was that, it would be a minimum, right? Negative, 0, positive. But it's neither, right? It's neither. So this also says not a relative max or min. So the first derivative test conclusively tells us that's not a minimum, it's not a maximum. Whereas the second derivative test sort of just failed, okay? Because it is possible that the second derivative test fails, but the first derivative test does come up with a relative max or min. But bottom line is, that's it. We have one relative min, and we don't have any other relative max or mins. We do have a poi. Again, that's next video we're going to do. We do have a poi, and this ends up being a poi. That's why you see this happening. And I kind of hinted at how to test that. But that's all they asked. They only asked for relative min and max, so I'm going to actually stop the problem here and end with just this p. When t is 5, we have a relative min. And of course, you could plug that into the original equation. I'm not going to bother. Plug it in and get the actual y value, or in this case, the p value of that minimum, and get the point. All right. So pretty straightforward, other than the fact that the second derivative test fails, which I warned you about. Let's look at an actual AP problem, and I'm going to leave this to you for homework for my class. So here's an actual AP problem, and I'm going to give you some hints because it's the first time you're seeing one, just to show you that it's never really that direct, right? Like we just did, or only maybe in the multiple choice, not so much in the free response. Okay, so we have this function f here that they're showing us. We have this function f, and they are talking about another function. So that we have this function f, and then later on they're talking about let g, this function g, be the antiderivative. Okay, fancy word for saying integration, right? Antiderivative of f. Okay, and if we go back to our tractor, for those of you who've seen my tractor video, right, that would make f kind of be the velocity, right? F would be the velocity because we're going to look at a graph ahead of it, right? And g is the antiderivative of it, right? That would be sort of the position graph, okay? So if you're thinking of the tractor, that's what we would discuss in comparison. So there's more than these questions, but I just took out the two that you can do, okay? So notice what they're asking you for. They're asking you for a relative maximum of g. Really, 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 really important, right? So you look at f here, and your temptation is to say, oh, this is a graph of the function they're asking about. Nope, this is the derivative graph, right? This is g prime, right? This is g prime. They don't write that, but we know that from our quick tractor discussion here. We know that from the fact that g is the antiderivative. So really, f is g prime. F is g prime, okay? And they want you to find all the values where g has a relative maximum. So I'm going to leave that up to you. You know how to do that. It's really the first derivative test because this is the first derivative. This is the first derivative of g. So see, by looking at the g values here, can you figure out the answer to that question? And don't forget to justify your answer. So you have to say why you know that that's a relative max or min using the first derivative test. Okay? And then for part B, it says, on what open intervals contained in -3 to 3? So only, again, and what you see here, is the graph of G, again, the original graph, is it concave up? Concave up. So you'll need, right, you'll need to examine what G double prime is, which they don't give you. They don't give you. They give you G prime, right? They give you G prime. So you'll have to figure out what's happening on the G double prime graph that would determine when there's concavity. Okay, so it's really the second derivative test, but it's also about the poise, right? So we did talk a little bit about the poise. This is really more about poise, but you can figure this out. So I want you to think about it, try it, and then when you come into class tomorrow, we'll go over this one.